Welcome back to ChemCore. This is the first video of Unit 2 of our Organic Chemistry course. Last unit, one of our last topics covered orbitals and bonding, and we talked about the differences and definitions of sigma and pi bonds. Before we talk about how this becomes important again, let's define a new concept. In organic chemistry, we talked a lot about isomers, or compounds that have the same molecular structure but different chemical structures. There are a couple different types of isomers that we cover in organic chemistry, but for now let's talk about the most basic type, constitutional isomers. Let's say that we have butane, or C4H10. We can draw butane in its stretched out chain form with no branches. However, we can also move this carbon around to form a branch. This is still C4H10, but it obviously looks different. Isomers are important not only for how they end up looking, but for the different properties and reactivities. In fact, we even have different names for some hydrocarbon isomers. For example, the isomer we just drew is iso-butane. Practice is important for drawing and evaluating constitutional isomers, so make sure to check out my practice problems and explainer videos linked below. Now, let's take a carbon-carbon double bond. As we talked, we would have an overlap of s orbitals, forming a sigma bond, and side-to-side interactions of p orbitals, forming one pi bond. Let's compare this to just a carbon-carbon single bond, which has only a sigma bond, using some real-life examples. Here, you can see two fists touching each other, like a fist bump. This will be our sigma bond, as it overlaps. I really suggest you follow along with your own fists. As you can with your own fists, we can rotate them about each other without separating them. Translating to chemical terms, the carbons connected by a single bond can rotate about each other. In other words, we say that our carbon-carbon single bond displays free rotation. However, if I were to reach out the thumbs on each of the fists and touch them, forming a pi bond, it's not so easy to rotate anymore. I can't move around the sigma bond without breaking the pi bond. In chemical terms, carbon-carbon double bonds cannot rotate about each other, meaning they don't have free rotation. The same is for triple bonds. For this next form of isomers, we're going to focus on carbon-carbon double bonds. Since carbon wants 4 bonds, each of these carbons is going to have 2 other single bonds. Let's say on each side of these bonds connects a chlorine, and the other connects a hydrogen. Well, we just said there's no free rotation around the carbons, so whichever way the molecule is drawn is the way it must stay. In the molecule we drew here, the chlorines face the same side, or up. We can also draw this molecule with the chlorines facing opposite sides. These molecules are isomers. The molecule on the left is a cis isomer, and the molecule on the right is a trans isomer. In conclusion, we call this type of isometry cis-trans isometry. Cis-trans isometry is exclusive to double bonded carbons. Single bonded carbons would have free rotation, so the groups can just move around any which way. Triple bonded carbons will only have one group and appear linear, so we can't really compare them. Also, to have cis-trans isometry, we must have 2 different groups on each of the double bonded carbons, but also a group that is the same. For example, if we had 2 hydrogens bonded to the left carbon, we wouldn't have cis-trans isometry, since we have no groups to compare. If we had all different groups connected to the carbons, we also wouldn't have cis-trans isometry, since we also don't have any groups to compare. When chemists draw cis-trans isomers in bond line structures, we have a way to draw them that makes the difference clear. A structure drawn with the double bond in a usual zigzag position shows a trans double bond. However, if we were to draw the double bond like this would show a cis double bond. Another thing I'd like to mention is that we can only determine if a molecule is a cis or trans is when it is drawn out. If we only have a molecular structure, we can determine that cis-trans isometry can or cannot exist, but we cannot determine if the structure is specifically a cis or trans isomer. In this video, we used orbitals to explain cis-trans isomerism, and we talked about constitutional isomers. In the next video, we're going to begin our conversation about functional groups, beginning with the simplest type, hydrocarbons.